In this video, we will explore the fundamentals of differentiation. First, we'll begin by understanding the meaning of this symbol. What is the meaning of this? It means that the limit of function f(x) as x approaches the value of a is equal to L. Next, let's talk a little bit about differential calculus. This is an area of mathematics that deals with rates of change. In particular, it deals with instantaneous rate of change. Instantaneous rate of change is basically the rate of change at a particular instance. And we're trying to find out how the dependent variable y changes as x, which is the independent variable, changes. When you do differentiation, you'll come across this symbol very often. So what exactly does dy dx mean? Now this is the most common symbol representing differentiation, but of course there are other symbols representing this differentiation as well. We will talk about that later. What it basically says is, it is defined as the instantaneous rate of change of y with respect to x. Now notice y is at the top, x at the bottom. So it tells you how y changes with respect to x. Now here we have a linear graph. Because dy dx tells you the slope or gradient of this straight line graph, it will be a constant. And the reason is because throughout this straight line graph, the slope remains the same. Therefore, dy dx of this straight line also will be equal to constant. If the graph is a curve instead, then what do you expect your dy dx to be like? Here we have a curve. Now notice that throughout the curve, the gradient changes. It is not constant like in the linear graph. Therefore, we will expect dy dx to be a variable. It will keep changing because the gradient is changing all the time as x changes. Now let's explore a graph that is non-linear and see what happens. Let's draw the two axes. Here is the curve. The curve takes the equation of y equals to function f(x), where function f(x) is just any function that defines this curve. I'm going to take a point, P, and I'm going to draw a green tangent line through point P. I am then interested to find the dy dx at point P. The dy dx at point P is basically the gradient of the green tangent line at point P. So that means I'm interested to find the gradient of this tangent line here. Now I'm going to take another point over here. So the first point P has the x coordinate of a, and the second point here has an x coordinate of a plus h. And that tells me that the distance between these 2 points is basically h. Next, I am going to find the corresponding y values. So since this x value is a, the corresponding y value will be fa. And since this x value is a plus h, what do you think the corresponding y value is going to be? Correct, fa plus h. Now that I have 2 points, one is P, another point is just arbitrary point that I took just now, I'm going to draw a red secant line through both points. Remember in your secondary school when you learn mathematics and you learn about coordinate geometry, do you remember how to find gradient of any line? The gradient of any straight line is basically rise over run. In this case, it will be finding the difference of y1 and y2 divide by the difference of x1 and x2. So I get this. This is my gradient of the rate secant line. Okay, so far? Now, as you can see, the red secant line that I have here looks totally different from the green tangent line, whose gradient I am interested in. So, what I'm going to do next is to try and make the two lines more similar. So, same curve again, same point P, same green tangent line. But now notice I've shifted the other arbitrary point closer. This is still A and this is still A plus H. But the H is now smaller than before. If you realize, the 2 points are closer now. FA will be the Y value of the first point. FA plus H will be the Y value of the second point. Now, let's draw a rate secant line again. Over here is the rate secant line joining the 2 points. Again, let's find the gradient of the rate secant line. It is still rise over run, so it's still this formula. Now, do you notice that now that the H is smaller, the more similar is the rate secant line to the green tangent line? Just now in the earlier graph, the rate secant line was quite different from the green tangent line. Now that I've moved H to be smaller, the two lines are more similar, though still not the same. So, let's shift the point again. Here are the axes. This is the curve. The same point P, same green tangent line, but now I've shifted the other arbitrary point even closer now. A plus H. The distance between them is H, and H again has become even smaller. The Y values are FA plus H. Now let's draw the rate secant line once again. Now what do you notice? Isn't the rate secant line even more similar to the green tangent line now? Gradient of the rate secant line is still rise over run, so it's the same old formula. Again, do you notice that the smaller the H, the more similar is the rate secant line to the green tangent line? Now I can keep on drawing and drawing, but here is the conclusion I'd like to lead you to. That to find dy dx, it is basically finding the limit of the gradient of the red secant line by letting H approach 0. This is the fundamental basis of differentiation. We are not going to have to prove this in any form, but this introduction is to let you understand what is the idea behind dy dx. Some remarks to conclude. Firstly, if your change in x is small, then dy dx is a good approximation for change in y over change in x. Now you notice that in the graphs earlier, that when I shift the 2 points to be closer and closer, when the change in x is small, dy dx will be approximately the same as change in y over the change in x. Remember how the red secant line becomes more and more similar to the green tangent line. Differentiation is also known as the process of finding the derivative or the gradient of a function. So, if a question asks you to find gradient, what you need to do is to perform differentiation. The derivative of a non-linear function will be a variable. This is because the gradient keeps changing throughout the graph. We've talked about this just now. You may see different symbols of derivatives. One possible way of writing differentiation is f prime x. Basically, you write f with a little apostrophe at the top, f prime x. This also means to differentiate function fx. Again, depending on what's the dependent and the independent variable, you may see other forms of differentiation symbols such as dr dx, dz dt. Now, taking dz dt as an example, z will be the dependent variable and t is actually the independent variable. So different differentiation symbols can be used depending on the dependent and the independent variables.